On this question then, we need to take measurements from the diagram. We'll need a protractor and also a ruler. So what I'd always recommend is getting the lengths drawn on. We're choosing our pivot at this point just here, and using a ruler on the bit of paper. I think from memory that was roughly 14 centimetres, but in the question it says that there's a scale 1 to 10, so 14 centimetres really means it's 140 centimetres, which we can change that and convert it straight into metres, which then gives 1.4 metres from there. And I believe that from here to here, our distance was 4.4 centimetres, which is then 44 centimetres, which is then 0.44 metres. We've now got all of our distances, and now we need to work out what our forces are and then linking that to moments. We know that this force has been given to us and it's already at right angles. As a reminder, moment equals force times a perpendicular distance from the pivot. So we have a distance along here and it's at right angles. We don't need to do anything with that one. However, we do need to look at the muscle force. I'm going to call that one F, and that's what we're trying to find if we read the question, the size of the muscle force. However, that is not at right angles, and you need to use a protractor. We're trying to find what the value is just here that is at right angles. It's not quite right angles, but we'll have to go with it because it's hard to draw a right angle on here. With a protractor, you should be able to see that that is about 30 degrees. We now need to think about Pythagoras. We know that the muscle force has got to be our hypotenuse. We're trying to find the value that's the arrow that I've just drawn, which is then the adjacent. So we're going to use cos, because cos equals adjacent over hypotenuse, or cos theta equals adjacent over hypotenuse. Like we said, we're trying to find the adjacent value, the one that's at right angles to the pivot. We can then multiply that up. So we've got the hypotenuse equal, or hypotenuse multiplied by cos theta, and that's then equal to the adjacent value, which is the one we're trying to find. The hypotenuse, that is now our force F. So F cos 30 is our value. We can now start taking moments now that we've got all of our key information on there. And as a reminder, moment equals force multiplied by perpendicular distance from the pivot. We've got our force there and our distance. So the first thing will be to do 6,500 multiplied by our distance, which is 1.4, and then we can put that equal to our other force, which we said is F cos 30, and of course F is the number we are trying to find the value of, and our distance from the pivot, so it's the force is coming up from there, so our distance is our 0.44. We can now start to simplify that. 6,500 times 1.4 gives us our 9,100, and that of course still equals the F cos 30 times by our 0.44. If we now simplify the other side, cos 30 times 0.44 gives you 0.38, and then finally rearrange 9,100 divided by 0.38, and that comes to an answer of 23881 newtons, but to a sensible number of significant figures, there's two significant figures that we've used elsewhere, so 24,000 newtons. For this next one, there's a couple of ways of approaching it, but I'll go through one of the ways, and it's just a case of writing on some key information first, using sine, cos, or tan, applying that to moments, and then finding the unknown. If we read the question, we know the mass of the trolley and paving stone is 18.5 kilograms. Well, the first thing to do is we need that in terms of force. If we put that into our calculator, 18.5 times 9.8 gives us a value of 181.3 newtons. We know the length of the trolley, that's 0.97, and the force on the handle, so that's this one, is then 50 newtons. Now, our job is to determine the distance from the centre of gravity of the loaded trolley from the wheels. We're trying to find this distance here that I'm going to call x, but at that distance x, that's where we're saying our centre of mass is, and therefore our centre of gravity, and that is therefore 181.3 newtons. Okay, we're not given any angles, but as you'll see in a minute, they cancel. I think it's important to show that they cancel. So if we just do them one by one, as per usual, we know that moment equals force times perpendicular distance from the pivot. And we know that clockwise and anti-clockwise moments, or the sum of the clockwise and anti-clockwise moments, equal each other when in equilibrium, which this suggests that it is indeed in equilibrium. If we start with the slightly easier one maybe, let's start with the 50 newtons and work out what the anti-clockwise moment is there. So that one's forcing it round the pivot, which is here, in an anti-clockwise direction. We're trying to find the force at right angles to it. The 50 newtons will be our hypotenuse. Therefore, we've got an angle inside just here that I'm going to call theta. If we start labeling it, we know that this is the hypotenuse, and then this side just here is the adjacent, which is the one that we're trying to find the component of. And we know that cos theta equals A over H. We're trying to find the adjacent, so we need to move the hypotenuse up. So therefore, it's hypotenuse cos theta equals the adjacent. And we're trying to find the adjacent as a reminder, because that's the one at right angles to where our pivot is. The hypotenuse, well, that's the same as 50. So therefore, it's 50 cos theta, which is our force. So it's really important that remember that is our force, our perpendicular force. If we then move down to the dotted lines at the bottom, where I've got the green arrow, we know moment is force times perpendicular distance. We're saying the force in this direction is 50 cos theta, but then our distance, well, that is 0.97 meters away. We now need to do exactly the same, but in the other direction. And this time, what we're trying to find is, again, the perpendicular force. We want the force that's going in that direction. And again, our angle here is the same, it's theta. So it's going to be cos again. This time it would be 181.3 cos theta. And then our distance this time, well, we don't know it, so we're going to leave that one as x. Because clockwise moments equals anti-clockwise moments, we can write those equal to each other. So 50 cos theta times by 0.97, and that equals 181.3 cos theta times by x. As we mentioned earlier, the cos thetas cancel because they're on both sides of the equation. And now it's a case of simplifying what we've got on the left-hand side and the right-hand side, and then rearranging to find the unknown. So on this side, 50 times 0.97 is 48.5. And that's then equal to 181.3x. So x equals, well, they're multiplied on this side, so we need to divide. So that's then 48.5 divided by 181.3. And that gives an answer of 0.27 meters. For question number 3, so we need to show that the maximum weight of the base is about 870 newtons. We're told that we've got a capacity of 85 litres of water, so we're going to have 85 times 1, which of course equals 85 kilograms. We need to remember to add on the base. That's then plus 3.5. So I think some quick maths tells us it's 88.5 kilograms. But of course, the value of gravity, we need to convert mass into gravity. So that's mass times gravitational field strength. 88.5 times 9.81 gives an answer of 868.185, so 0.2 newtons, which is pretty close to 870. Moving on to the next part, we've got then it on a tilt, and we've got some numbers. This looks like a moment question, so I think it's probably a good idea to start writing some stuff on there. I've copied it across so we can see it next to the question. Calculate the minimum force of the wind that will cause the basketball set to be blown over when it is at the angle shown. Ignore the effect of wind on the base. And then we've got the weight of the post arrangement is 27 newtons. So let's write some stuff on that we can identify. I've drawn the dot just here for the pivot. We know the weight is 27 newtons. And we now need to start working through the clockwise and anti-clockwise moments. So we know force times perpendicular distance. We're going to have to work out some perpendicular distances or perpendicular forces, one or the other. And secondly, remember that anti-clockwise moments, or the sum of them, equal the clockwise moments as well. It's just a case of choosing where to start. Let's start bottom right with the weight of the base. We can see that it's all at an angle, so we need to find the component of the force which is at right angles. And because of what we've got written just here, we can identify that as 15 degrees as an angle. And we know that that's a right angle just here, and the weight of the base is therefore the hypotenuse. From the previous question, we know that that's 868.2 newtons, assuming it's full of water. We can therefore work out what the moment is in that direction. Again, this is the hypotenuse just here, and we're trying to find the one at right angles to everything. So we're trying to find the adjacent. So cos theta equals adjacent over hypotenuse. Hypotenuse is the weight of the base, which is our 868.2. So 868.2 cos 15 equals our component of the force that's at right angles to the distance from the pivot. If we put that into a calculator, we get an answer of 838.6 newtons. But we need to remember that's still a force. We need to turn it into a moment, and we do that by multiplying it by the distance, which is 0.45. If we then look at the moment going in that direction, that's pulling it round in that direction, clockwise, we can say the force is 838.6, and then the distance away is 0.45. So multiply that in, so we have a moment of 377.4 for that one. Are there any more going around in that direction? I don't think there are. Okay, so now let's look at the other direction. Well, we've got this one here that's pulling it round that way. And this time we've got to find the perpendicular force that's caused by that. So that's coming out in that direction. and then turn that into a right angle, just there. So our angle is going to be 15 degrees again. This time though, we're trying to find this value because that's the one that's at right angles to the pivot. That is therefore the opposite. We've got the hypotenuse that is our 27 newtons. So sine theta equals opposite over hypotenuse. So we want to try and find the force, which is the hypotenuse 27 multiplied by sine 15, bringing that one up. And that gives us the value for the opposite, but we need to remember that's not yet a moment. We need to multiply that by the distance, which is 2. So whack that into a calculator. 27 times sine 15 and multiply that by 2, which gives an answer of just under 14, 13.98 Newton meters in that direction. But we've got an additional one just here, which we need to now calculate. We know that one side equals the other. So if we find the difference between the two of them, that tells us the total moment in that direction. Once we have the moment in that direction, we know how far away it is from the pivot. We can then work out the size of the force. Crikey. So what is that then? 377.4, take away 13.98. The moment that we're missing, 363.42 Newton meters is our moment. Now, that of course is force times perpendicular distance. So that moment is being caused by that force just here. And we then need to find, crikey, the force of the wind. I'm going to redraw that triangle slightly so we can see it a little bit clearer. So we know that we've got the force there. This is our moment. And we know that angle is 15 degrees. We know this distance down here, well, we need to be careful because it's 2 multiplied, so it added together to 0.4, so that distance is 2.4 meters from the pivot. So the moment equals force times distance. The moment we said is 363.42. We need to divide it through by the distance, 2.4, and that will give us this force just here, the one that's at right angles, which then gives us a value of the force being 151.43 newtons. This one, the component is always the hypotenuse. This one's the adjacent, so we need to use cos. Theta is adjacent over hypotenuse. The adjacent we said was 151.43. We're trying to find the hypotenuse. That one goes there, that one goes underneath. So hypotenuse equals adjacent divided by cos theta. The adjacent is 151.43. Divide that by cos 15, and that should give us the size of our force that we're trying to find out. So divide that by cos 15, and the answer is 156.8 newtons. Okay, let's clear some space so we can read the next question. That one did go on an awful lot for what is 3 marks. That was not an easy question at all. If we read then the next one. So the base is filled with sand instead of water. The density of the sand is greater, so therefore the mass will be greater. Stating to justify what would happen to the value of Fw, so that's the force in the wind calculated in part B. Well, If it's got a heavier base, it's going to be more sturdy. Therefore, Fw will need to be greater, but we need to state and justify what's going on. So the easiest thing here would be for me to paste in the mark scheme and just show you it so I don't have to write it out. The second mark is then saying that the weight of the base would increase and linking it to the idea of moments, which then of course increases the moment in this direction, which means the moment in that direction would have to be a lot greater. For the next one, we've got a person on a ladder propped up against a wall. Again, this could be quite tricky. We need to make sure the arrows are all sorted so we know exactly what's going on, all of the extra weights, and of course which force is pushing in which direction, because it's going to be another moments question. Let's take a look. Okay, complete the diagram by labelling the other three forces acting on the system. Well, just to save my pen, I've copied in the mark scheme. Most of them should be self-explanatory. Sometimes you're expected to draw the arrows on yourself, so this is a good question for identifying the forces. You're looking for contact points, plus the one of centre of mass or centre of weight. So if we just look at the different labels, well, when you've got the ladder pushing against the ground, the one going up, of course, will be a normal contact force or reaction force. And the reason it doesn't slide this way is because friction is in the other direction, stopping it from sliding. Of course, this contact point, we've got another reaction force or a normal contact force with the wall. And of course, the one going down is the person's weight or the weight of the system. And then for part B, we need to use the principle of moments to explain why the system is stable. So we can then link now to moments, because if it's stable, then the conservation of moments anticlockwise, or the sum of the anticlockwise equals the sum of the clockwise moments. And then we need to identify why it will topple over if the angle gets too big. So it's going, and if you've ever climbed a ladder, you'll know the angle that you shove the ladder against the wall is quite important. Okay, so it's a 6-mark question. It's going to be quite mean. Let's go through how to do it. These are the 6 points. So the ladder is stable because the forces or the moments are in equilibrium. So we mentioned that briefly a second ago. However, the next one, when in equilibrium or stable, the clockwise moment of the normal contact force, so that's this one, is equal to the moment of the weight, which of course is that one, pushing down in that direction, and that's assuming that the pivot is just there. And of course, if the pivot is here, we could ignore that force and that force because there's no distance or no perpendicular distance from that point. The third one, again, is just what I've just said, is that reference to taking moments about the bottom of the ladder, so that's that bit. So we did imply it with our previous answer. The fourth one takes a bit of thinking about what it's meaning, but I'll show you in a second. If theta is large enough, the centre of gravity is now to the right of the bottom of the ladder. So as it gets steeper, that means the angle is getting greater. The centre of mass will keep moving to the right, towards the pivot. And the moment when the angle is big enough, so I'm going to do an exaggeration here, let's say it's going the other way, then the weight will start acting as a clockwise moment. And that's then what this one is mentioning just here, the 5th bullet point. If the angle gets too big, the centre of mass will start moving towards the right, and the point at which it passes over the pivot, that's when it will topple and the system will go in a clockwise moment. And then the last bullet point, if the mass is now causing a clockwise moment, there is no longer any more anti-clockwise moments to make the ladder balance out. So it will topple.